So, you see, nothing is more better than a course ending. It is always very nice when your course ends, and we are also happy as students that a course is ending. But when the course ends, we are in a much more advanced territory. So, here we are going to speak about infinite series, and I will be concentrating myself in studying a series of this kind. Whatever, and all of these numbers a k are positive numbers. Obviously, k is element of n, k is 1, 2, 3, 4, 5, 6, it just goes. Now, you might ask me why the hell I should study this? How can you get a series or this sort of strange thing that you add infinite quantities? Can you really add infinite quantities? Can you go on adding up to infinite times? It is not possible. It looks very strange, but I tell you that it is possible, and it comes from the very basic notion of movement. So, suppose I start from 0 and 1, this interval 0, 1. So, there is a road which is 1 kilometer or 1 meter, say, in this room. So, I am going from here to there. So, this is how Greeks proved that motion is impossible, but you know that motion is possible. So, if you want to go from here to there, what you do? You first go half of the road. So, you first go half of the road, so exactly in the middle. Then the half is remaining. So, your next strategy would be go to the next half of the road, and the next half is remaining. So, you go to the next half. So, between 1 and 1 and half and 1. So, you go to basically 3/4, and then between this you have another half, right. Go to this half, and again this part you have half, and again this part you have half. So, you make you are approaching this point 1. So, what is the distance now travelled by you? It is half plus 1/4, sorry, not half, this 3/4, this is 1/8. Sorry, 3/4. So, you have covered half. So, then you covered you covered half to 3/4. So, you have covered a distance of 1/4 kilometer. Then you covered a distance of 1/8 kilometer from here to here, half of this, and so on. So, you keep on doing it, keep on doing it, keep on doing it. So, here is the end. So, there is half of this, then you go, then half of this. So, distance between your current position and the final point becomes smaller and smaller, but you never reach that final point. So, you never reach that final point. So, now what I have done, so you have kept on adding it 1/16 and so on. So, basically what is this? This is half plus 1/4 plus 1/8 plus 1/16 plus. Now, so what the Greeks said, now come on, this so motion is impossible, you will never reach from that point 0 to 1. But motion is possible because I can always cover infinite steps in finite time. And what does this tell me? That there is, so you can tell me, does this sum add up to anything? What I tell you that if you can really go infinite times, this sum should add up to 1. This must be very surprising. infinite number of terms, though they are smaller and smaller, they add up to 1. I say yes, they add up to 1 because I am going from 0 to 1, and that is exactly what I did. So, if I can move on, go on infinite times, I will finally reach there. That is a tricky thing, to tell that if I have gone infinite times and I will reach there, I will never go infinite times. So, what does this meaning of this 1 as a sum of this? So, what is the meaning of sum of a series? So, you see this very basic, very ancient days, this whole idea came, this whole idea came. Now, infinite series occur in many situations in science. It's a very natural thing, and of course in mathematics. Now, what I mean by the sum of a series? So, what I mean by sum of a series. Now, it is very important to understand that we have just learned about sum of a sequence, the limit of a sequence. We have not learnt about a sum of a series. So, our route to anything that we do in analysis or advanced calculus, if you want to say, is through sequences. As I told you that this last week's lecture is actually taking you off from basic calculus into more advanced, into the advanced realm of analysis. So, sum of a series actually is done in following way. So, I will define what is called partial sums. So, partial sums is done in the following way. So, S1 is equal to A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. Similarly, Sn is A1 plus A2 plus An. Now, here we have got a sequence of partial sums Sn, sequence of partial sum. And Sn is Sn. Okay. Now, suppose limit of Sn as n tends to infinity exists and it is equal to S, then this S is called the sum of this series. The small s that I have is called the sum of this series. Similarly, you have to observe one thing, because these are all positive terms, S1 is strictly less than S2, is strictly less than S3, is strictly less than S4, and so on and so forth. So, what you get is that S of k is strictly less than S of k plus 1. So, it is a non-decreasing series, in fact, it is a strictly increasing series. When you have a strictly increasing series, we have just learnt yesterday in the last class that if this is bounded above, right, if this is bounded above, then it will converge and it will converge to the supremum. So, that is exactly what we have to say. We have just spoken about a bounded sequence, but okay, bounded sequence is both bounded above and below. So, here anyway it is bounded because it is always bounded by strictly bigger than 0, there is a lower bound. So, if it is bounded above also, so then it will converge and converge to the supremum. So, if this forms a bounded sequence, then I actually can speak about convergence. For example, if I take this Sn here, which is 1 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2n. This is your standard high school geometric series, GP series. So, if you are looking at the sum of those, these are GP series which you know from high school we have this. So, you have the common ratio to be half and then this is your sum. So, now what would happen if you take, in this particular case, if you take the limit of Sn as n tends to infinity, you know that half as n tends to infinity. So, this will become 1 by 2 to the power n. So, as n becomes infinity, 2 to the power n grows very large. So, this part vanishes in the limit. So, the limit ultimately becomes half into 1 minus half, which is equal to 1. So, the limit is ultimately 1. Now, you might be answering me that could you have observed that this is bounded? I would say yes, I could observe that all of these Sn's are actually less than equal to 1. Because of this very diagram, you will immediately see from the geometry that Sn is less than equal to 1. So, if you do not even bother about this, you know that this sequence actually converges because it is again an increasing series which is bounded above. And here we can actually tell what the limit is. So, the limit is 1 and so this writing which actually conforms with our intuition makes sense. So, mathematics always comes from intuition, that is something that one really has to keep in mind before we do anything. Any sequence, any series which does not converge, it could have that the sequence is unbounded above and it does not converge. And then what sort of thing would happen? Can I have so then it will not converge and hence then we do not have any sum of a series and then we call such series as divergent. So, let me give you a very interesting example of a divergent series which is quite the standard example which is given, but there is a little story behind it, but it is a very tricky and very nicely done stuff. This is called the harmonic series Hn, harmonic series H. You know, if I just take the sequence 1 half, 1/3, 1 by n, it converges. It converges to 0, that is what we have decided in the last class. But here it does not, this is a very strange thing that when you sum them up, it does not converge. It just does not converge, it blows up. So, how does one prove that? Its proof is very non-traditional. It is not trying to show that okay. So, how it needs a little bit of trick. So, idea is to show that my limit here Sn, limit of Sn does not go to a finite number, it blows up, it goes to plus infinity, that is what will be shown here. 1859, if I am not wrong, I will tell you how the little bit of history. In a beautiful city in France called Lille, L-E, something like this. Their head priest of the church, local church, Nicolas Orseme, died. But nobody knew that Nicolas Orseme was actually a mathematician. And one of his most enduring, apart from many other things, one of his many enduring contributions to mathematics is to actually show that this series is divergent. So, it was only discovered after his death that he had actually proved among his manuscripts this fact. So, what he said here, observe that suppose I take a partial sum with odd number, even number of terms and I prove that this is bounded by some b. then S1 plus S2 plus S3, sorry, this is also actually bounded. This is bounded by, also bounded by B. These are, because these are all positive terms. Sorry, A1, A2, I am not writing S1, S2, I am making a mistake, sorry, A1, A2. So, what I am trying to say is that if I take some positives, I mean I take for only even positive terms and show that it is bounded, then I can show that all the terms, all the partial sequence S4. So, if I say that S2 2m is bounded by B, then all the whole sequence is bounded by B, right. The whole sequence can be shown to be bounded. Then in the same way, the way we declared, because if I say I take first 4, S4 is this, is B, then what is S3? What S3 is? S1 plus S2 plus S3, which is less than equal to B minus S4, which is less than equal to B. Sorry, B minus A1, sorry, I made a mistake, B minus A1, which is less than equal to B. I think I am just making, again writing mistakes. So, A1 plus A2, so S3 is also bounded by B. So, if I just show that this is is bounded, then I can show the sequence is bounded. If I show that this is blowing up, this particular subsequence is blowing up, then the sequence is actually blowing up. It will be A4, B minus A4, B minus A4 is positive, so it is less than B. Now, okay. So, what was Nicolas-Orsemes proof? So, let us write down then Nicolas-Orsemes proof. This is very, very important. So, how did he prove? So, he took S2 to the power m, an even thing. So, you see first he has taken left the first term, 1 he has forgotten, then he joined these two terms 1/3 and 1/4. There is slight, you might get why he is doing so. So, I am giving you the proof from a book called Invitation to Classical Analysis by Peter Duren. So, I am writing, but this proof is very common, you can find it in many books. I am just writing the book which I am using to get this proof, but this is so classical, you can just do it. So, you have this series and what do you do? So, you will write this as 1 plus half. So, you know 1/3 is also bigger than 1/4. So, it is 2 into 1/4. 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, 1/7 is bigger than 1/8. So, it is greater than equal to 4 into 1/8 and so forth. So, it is 2 to the power m minus 1 times 1 by 2 to the power m, this last part is greater than that. So, here when you see when 2 cube, it is 2 cube here, m is 3. So, here it is 4 plus 1, 2 to the power m 3 minus 1, 2 square plus 1 3. So, this is the structure, general structure. Now, So, if I sum it up, so what do I get? 1 plus half plus 2 square. So, it is 2. This is half, right? This is 2 square 2 cube, this is half and this is half. So, how many times I have the half? M times 1 plus half. So, there are m minus 1 terms. So, this is half, 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 this is m terms here and this is 1. So, m times I am adding the halves. So, basically I will get 1 plus m by 2. Now, limit of s to the power m as m tends to infinity is equal to limit of 1 plus m by 2 as m tends to infinity is infinity. No, sorry, not equal to, greater than equals to. So, what is happening? That this sum, this sequence is always bounded below by some quantity and that quantity actually blows up, is bounded below by some series of this form and this series actually blows up, the sum goes up to is unbounded. So, what I am showing here that this sequence when I take a sequence, when I basically take a sequence, this sequence is unbounded. So, my sequence is bigger than a sequence which is unbounded. So, this cannot be bounded, unbounded below. So, this cannot be bounded below. So, its limit of this has to be infinity. This limit also has to be infinity. So, which means that this series does not converge, because the limit ultimately we will say that it has a sum, means it is a finite sum. But here there is a magic. I will change this game and write down to you the famous Euler series. So, Euler dealt with a series which is slightly different than this. What about this series? Is it convergent? This is a fascinating thing, that it is convergent. It has a sum which Euler found out, but Euler's proof is nowadays people laugh over it. Oh, it is not so rigorous. So, we do not understand what is rigor by our now, as I told you earlier, would not be rigor after 200 years. So, but Euler's insight was always right. So, insight is, again I tell you, is more important in mathematics than other things. So, let us see how this has been proved. So, here I have to prove that it is less than equal to some, the S2m is bounded by some number. So, the whole thing is bounded by some number, it is a positive sequence. So, it is an increasing sequence bound has an upper bound and hence it will, by our previous learning, it will converge and converge to the upper bound, converge to the supremum, need not be the upper bound, but to the supremum. Sorry, again S2m. So, how does S2m look like here? Same technique, you see, we are gathering these terms. The same ideas of Nicolas Orsem is also used here, 7. I am just using the book so that I do not, so I am prone to making mistakes. Because classical analysis, though it is pretty interesting, can become a little clumsy when you write. So, you have to be very careful. So, this is what is done. So, you know 1 by 3 square is also less than 1 by 2 square. because 4 is less than 9. So, what I get, this is less than 1 plus 2 into 1 by 2 square, am I right? Plus here 4 into 1 by 4 square plus it goes on to the power m minus 1, because there are 2 to the power m minus 1 terms here, into 1 by the first term, which is 2 into, you see 2 of half, 2 of 1 half square, 4 of 1/4 square, because all of them is less than 1/4 square, 2 to the power m minus 1 plus 1 by 2m. So, what I get? So, if you look at this again, it is less than equal to 1 plus half, this is 2 square, exactly 1 by 2 square, this is less than 1 by 2 cube and so on to 1 by 2 to the power m, but we have already studied the geometric series earlier, just this walking series. So, and that we know that this part has to be always less than 1. So, this total part has to be less than 2. So, this sequence always has an upper bound 2, and being a positive series will converge straight to its supremum. Now, 2 is not its supremum. What is its supremum? Euler gave a fantastic answer to this, and you should know this. This is one of the most brilliant results in all mathematics, one of the most beautiful results. Sometimes you do not always ask, how can mathematics be applied, how can mathematics be applied. Life is not interesting if it is just only bothered with what is necessary and what is practical. Life is important, life is interesting when it also is associated with something beautiful. So, here is a result which speaks about the beauty of mathematics, and you believe it or not, its supremum or its limit is a irrational number. It is pi square, pi, our favorite pi square by 6. This is one of the most important results in all mathematics. So, pi square is irrational. So, one can prove that actually. So, this is what happens. So, you see today we had a very nice idea with these two important class of series. So, what is convergence and what is divergence, and how we have used the idea of a sequence, how we have used the results of a sequence about sequences to talk about series and make meaning of the term the sum of an infinite series of positive terms. So, tomorrow we will speak more about the series, and the last two classes will be dedicated to Taylor's theorem, last 1.5 class, and maybe some history I will tell you at the end of the last class. So, thank you very much. I hope that you are enjoying it.